In this video, I want to talk about another application of derivatives. Specifically, I want to talk about using them for linear approximations to complex functions. Okay? Linear approximations are good because linear functions are simple, easy to work with. All right? Let me show you some common situations where linear functions are helpful. Okay? Suppose you had a equation you were working with that had lots of trig functions. Okay, specifically, let's say you had a sine somewhere in there. Okay, and suppose that you knew that the angle was very, very small. Okay. If you look at, I sketched out a small piece of the sine function. Notice that, let's zoom in on the part around the origin. Okay, can you see that if you focus just on this part very close to the origin, can you see that the sine graph can you see that it's very close to a straight line? In fact, it's very close to the line y equal to x. In other words, the line with the slope of 1, right? So for small angles, we would expect the sine function to give a value close to x. And in fact, that is what we see. You can investigate that yourself with the following. Take the sine of a small value like 0.00123. I'll bet you that if you do that on your calculator, even though I haven't memorized all the sine values, I'll bet you that that's going to give you something approximately equal to 0.00123. See that? Try the sine of 10 to the minus 4. I'll bet you that's going to give you something approximately equal to 10 to the minus 4. So what I just did was I made a linear approximation to the sine. So if let's say I had some huge theory that I was working with, like let's say I had 3 sine squared x plus 4 times e to the sine x plus sine x minus 9, something like, let's say, sine x minus 9. So if I knew that x was always small, I could just immediately simplify all that nightmare by replacing sine with x. So if I was doing some theory work, I might simplify this to 3x squared plus 4 times e to the x plus x minus 9. All right, a little bit nicer. In fact, if the x was very small, then that, let's say, was close to 0, you might even say that that an exponential function gets close to 1, so maybe you can even eliminate that. And look what we've done. We've successfully turned that nightmare expression into a quadratic, right? Well, we know how to solve quadratic equations, quadratic formula, and all of a sudden it becomes doable instead of impossible. Okay, so that's the power of linear approximations. So let me show you a cooked up example of how this could be useful. So we know that the square root of 4 is 2. Suppose I asked you for an approximation to the square root of 5. Now you know it's bigger than 4 perhaps, but what is it? 4.1? Is it closer to 4.3? Can we make a little bit more progress than just saying it's 4 point something? Okay, let me show you how you could use derivatives to get a better approximation. So let's make a sketch of the square root function, and you should know the general shape of what it looks like. The general shape of the square root function. So we know that that function goes through the point 4 comma 2, right? So we have this red dot all taken care of. Okay, what we are basically trying to do is we are trying to find the height we're trying to find the y value of the green dot at x equal to 5. Okay? So taking the square root of 5 is not easy. However, we learned how to find the equation of the tangent line, didn't we? What if instead of finding the value of the green dot on the square root function graph, what if instead we found the value on the tangent line? Now, that's not going to be exact, but it's going to be pretty darn close. I think you would agree that that orange line, the tangent line, looks like it's going to be about the same height as the green dot when we are at x equal to 5. Okay, so and that indeed is what we're going to do for our linear approximation. So let's get the tangent line to the square root function going through x equal to 4. Okay, so the square root of the tangent of the square root, the derivative of the square root function is 1 over 2 root x. If I plug in 4, I get 1 over 2 square root of 4, which is 1/4. So the tangent line is 1/4 x plus b. And if I plug in the 0.4 comma 2, replace x and y with those specific values, I get 2 equals 1/4 4 plus b. So b is equal to 1. So the tangent line apparently is y equals x over 4 plus 1. Now the rest of it is all downhill. So now plug in x equal to 5, and if you do that into the tangent line equation, we're going to get 5 over 4 plus 1, or 2.25. So you can punch in your calculator what the square root of 5 is, get the decimal, and I'll bet you're going to get something close to 2.25. All right? Isn't that wonderful? So we can do complicated calculations, at least approximately, by using derivatives in our tangent line approximation. All right? Let me show you let me explain the same thing in a slightly different way that might be useful to you. All right? It's still going to be the same idea. We're still going to be using linear approximations to complicated functions, but I just want to give you a different treatment that might be a little quicker. So at the red dot, the tangent line has a slope. The slope is delta y over delta x, just like it's true for all functions, all lines. Okay, and we were able to calculate the slope of that tangent line using the derivative. So the derivative of, in this case, the function was square root of x, but in general it'll be some f, and then so the derivative is f prime of x. And we can find the change in y between the red and green dot, that's delta y. If I cross multiply with the red equation that I just wrote down, I get f prime delta x, right, times delta x. And so now this gives me the change in y along the tangent line, not along the square root graph. All right, but all of this is to say that the change in y along the square root graph is approximately the derivative times the change in x. Okay, so in other words, what I'm trying to do is I'm trying to boil down what I just did of using the tangent line to a very simple compact equation. Okay, and this of course is the same thing, it's just in a different format. So for example, the square root of 4 was 2. We want to know how much extra we have to add to 2 to do the square root of 5, right? So we're looking for the delta y. That's going to be approximately f prime at 4, and then delta x is 5 minus 4. So that's going to be approximately the derivative at 4, which was 1/4, or 0.25. So you add 0.25 to 2, and again, you get 2.25. All right, so that is one example of approximating complicated calculations with derivatives.